Welcome, everyone. Let's jump right into today's explainer because we are looking at a massive, absolute paradigm shift happening right now in the world of self-driving cars. You know, for the better part of a decade, we've kind of been stuck in this almost there phase, right? The industry has been chipping away at the problem using one very specific playbook. But recently, the script got completely flipped. We are officially moving away from rigid, hand-coded rules and moving toward machines that are literally learning to understand the physical world all on their own. It is a wildly fascinating evolution, and I am absolutely thrilled to unpack it with you today.
Okay, let's dive into this. 300,000. Just take a second to really process that number. 300,000. That is the staggering amount of human-written lines of C++ code that Tesla recently just deleted from its self-driving system, completely scrapped. For years, engineers spent countless hours trying to brute force the act of driving by meticulously writing rules for literally every possible scenario. They essentially believed driving could be solved like a giant math equation. And now, all of that core logic that previously dictated exactly how the car should behave, decades of incredibly complex engineering, is just gone. It's been replaced by a completely different approach.
This quote from Elon Musk actually sums up the sheer magnitude of this shift perfectly. He notes that in their new system, there is no line of code that explicitly tells the car, hey, there's a roundabout here. And honestly, that makes total sense, because hard-coding if-then rules for every single weird, chaotic real-world scenario, it's fundamentally impossible. Think about it. A plastic bag blowing across a dark highway at dusk, or a cyclist making totally unpredictable, erratic hand signals while trying to balance a cup of coffee. The real world is just infinitely too messy for traditional programming to anticipate the whole shebang. Which brings us to Section 1, the problem with rules, David versus Goliath. We are witnessing a massive philosophical clash right now between traditional legacy automakers and a completely new, nimble, AI-first approach that's challenging everything we thought we knew. So there is a stark contrast splitting the industry right now. On one side, you have the traditional approach, championed by companies like Waymo. They rely heavily on explicit code, extremely expensive LiDAR sensors, and these centimeter-accurate high-definition maps. But then, on the flip side, you've got the neural network approach used by companies like Tesla. This relies on a vision-only, end-to-end AI system. Instead of being programmed, the car's behavior is learned organically from millions of human examples. It's a fundamental divergence in how we even tackle the problem. And the limitations of that older, traditional, rule-based approach, well, they're becoming glaringly obvious. Sure, these systems offer really transparent decision-making, but they are incredibly brittle. They fail the absolute moment they encounter a novel situation. Imagine a construction zone where a traffic cone just happens to be sitting upside down on top of a stop sign. A rule-based system just doesn't know what to do because no engineer sat down and wrote a rule for that specific absurdity. It completely lacks natural emergent behavior, the ability to just figure out a new solution on the fly. Plus, relying on HD maps means you need $100,000 sensor suites just to painstakingly pre-map cities, making it financially impossible to quickly scale to every random dirt road out there. That leads us right into Section 2. Enter the world model, giving cars imagination. This is the core academic concept straight out of recent research that's completely revolutionizing how vehicles process their environment. So let's define what we mean by a world model, which is also sometimes called physical AI. Simply put, it's an AI's ability to visually predict how the physical world is going to change based on its actions. It's exactly like human intuition. When you're driving and you see a bouncy ball roll into the street, your brain instantly goes, okay, a kid might be chasing that, and you hit the brakes. You intuitively understand the physics and behavioral patterns of the world. A world model is a generative neural system that lets a vehicle literally rehearse these kinds of features in its mind before it ever actually acts in reality. How crazy is that? Building on that incredible foundation, we have VLA, which stands for Vision, Language, Action. We're moving entirely away from vehicles that just blindly execute lines of code toward a single, unified brain that genuinely understands physical reality and context. And you might be wondering, wait, why is language involved in driving? Well, it's because the system can process prompts and grasp nuanced context far beyond just looking at visual pixels. It can understand a really complex command like pull over safely near the red brick building up ahead and seamlessly connect that language to the physical environment it's navigating. Okay, let's move on and see how this builds into complex decision-making, which happens in 3 remarkably elegant steps. First, the system compresses all that overwhelming raw sensor data into a neat, compact mental representation of the world. Second,
It imagines the future by rolling out hypothetical scenarios in a virtual sandbox. In literal milliseconds, the car is continuously generating thousands of possible futures, internally testing out different steering angles and braking pressures. And third, it actually plans its trajectory based on the absolute safest of those imagined outcomes.
A really fantastic way to conceptualize this whole thing is calling it ChatGPT for cars. We all know that ChatGPT doesn't actually know facts like an encyclopedia, right? It just predicts the next best word based on massive patterns it's studied in text. Well, this vehicle AI works the exact same way. Just like language models learn to write by studying human language, this AI predicts the next best steering angle or braking pressure based on billions of human driving patterns. It just naturally figures out the unwritten, unspoken rules of the road simply by watching humans drive for millions of hours.
Let's jump to Section 3, Training in the Matrix, Simulating Edge Cases. Because the big question is, how do you train an AI for the really dangerous stuff, when rare edge case crashes just don't happen often enough in real life to provide good training data? And this brilliantly illustrates the sheer scale of what we are dealing with here. 1.5 petabytes. To put that massive number into perspective, 1.5 petabytes is the equivalent of watching high-definition movies continuously 24 hours a day for over 3 centuries. Tesla's pipeline processes this unbelievable amount of video using 48 different neural networks, and it takes 70,000 GPU hours for just a single cycle. The massive, unprecedented computing power required to train these models is truly mind-bending. But processing all that data is really only half the battle. The old way of doing virtual simulation was a major bottleneck. You had to rely on traditional graphics engines, where human engineers and 3D artists would literally take months to painstakingly manually build out 3D cities and scenes. If they wanted to simulate a rainstorm, somebody had to go in and code the raindrops. Today, we've entered the era of generative simulators. Here, the AI learns physics directly from video data and builds these massive, complex environments completely automatically in a fraction of the time. Now, what's really interesting about this is an insight from Sonia Fidler, NVIDIA's VP of AI Research. With revolutionary projects like Alpa Dreams, developers are basically just learning simulation straight from data. They are creating these interactive, real-time simulated worlds that aren't just static backgrounds, but dynamic environments that adapt instantly and realistically to whatever the AI agent decides to do. The power of these generative simulators is an absolute game changer. They can reconstruct fully interactive 3D scenes from simple 2D video recordings. They can whip up extreme weather on demand. And they allow for interactive what-if testing in 100% complete safety. And this matters directly to you. This is the exact reason why, one day, you'll be able to sit comfortably in the backseat of a car reading a book while it navigates a massive blizzard. You will trust it because that AI won't panic. It will have already successfully driven through millions of simulated blizzards before its tires ever touch real snow. Moving to our final part, Section 4, Physical AI Frontier, the ultimate endgame. We need to zoom out here and discuss where all of this is heading and the significant hurdles that are still left to clear before it's everywhere. Because, look, the tech isn't perfect yet. Handling unpredictable black swan edge cases is still incredibly difficult. A black swan event is something totally bizarre, like a massive sinkhole suddenly opening up, or maybe someone in a T-Rex costume riding a unicycle down the middle of a highway. Those are inherently hard to train for. Additionally, safety regulators are demanding transparency, and they really struggle to accept the black box nature of AI decisions, where you can't explicitly trace the logic. And eventually, these models must also learn to integrate touch, so they can deeply understand ground dynamics, and audio, so they can hear critical things like an approaching emergency siren. So, the crucial, overarching point is this. We are moving firmly into the era of Software 2.0. We are replacing rigid, explicit programming logic with learned behavior. Folks, this isn't just a standard software upgrade. It's a completely different relationship between humans and machines. We're shifting away from dictating every single meticulous instruction. Instead, we are simply teaching a system how to learn. It is a profound shift in how we build and interact with technology. Which leaves us with a truly fascinating question to ponder. When AI completely masters the physical rules of driving, what else is it going to drive? A car learning to navigate a busy city is really just step one. Soon, humanoid robots could learn incredibly complex tasks, like manufacturing, cooking, or even assisting in surgery, just by observing us. Take a second to let the gravity of that sink in. It is an incredibly exciting shift that will absolutely redefine our relationship with the physical world. Thank you all so much for joining me on this deep dive explainer today. I truly hope you found it useful, that it sparked some curiosity, and that you learned something new. Catch you next time.